The title of my presentation is Thermodynamics for Environmental Stewardship, and it's basically how to design systems and how to use thermodynamics to design better systems. At least that's what Hervé asked me to talk about. But I was inspired a little bit yesterday by the last speaker, because he mentioned that he was creating an archive with lots of viruses and the development of viruses over time. And I remembered recently when all these lockdowns and things like that started, also in the UK where I live at the moment. I had a phone call or phone conversation with my sister, and she said, "You must be very busy with all this virus things and things like that." I said, "Well, no, I'm a microbiologist. I know a little bit about microbes, bacteria, and archaea, but I don't know anything about viruses." But then I thought, actually, I know that archives are very important, and it's important to store your data, so maybe later on you can reanalyze data or samples by using methods and methodologies that are not available at the moment you archive your stuff, but science develops and we know more and we get better techniques, so over time maybe you can do something useful with those things. Well, and for some reason they even published it. So this was basically what I wrote in a couple of hours. But the reason why I dare to say these things is, before I moved to the UK, I was in the Netherlands, because I'm Dutch, you can tell from my accent. And in the institute where I worked, we had a very big archive, a large archive, with soil samples, like how many? 250,000. Well, that's a lot of samples, but it also costs money to maintain these things and to maintain the storage for it. So they were wondering, should we really keep all those old samples or just throw them away? They were soil samples, and they had just basically air-dried the soil samples for future chemical analysis, because when methods became better. But then we were microbiologists. We thought, well, maybe we can also use those stored samples for microbial analysis. So that's what we did. It was in the early 2000s, so we had only DGGE. Sequencing was not really available yet. So we analyzed those soil samples, and we took 2 batches of the same soil, one that had been given animal manure and another was inorganic fertilizer, and you could really tell the difference between the 2 soils. So that's microbiology. You could, well, based on DGGE, you could distinguish the samples. So, okay, we thought this is something new. We sent it to science, and science said, wow, just a letter. Okay. But then I moved to the UK, and there I had, of course, new colleagues, and those colleagues were working on antibiotic resistance. And, well, we were discussing, well, maybe we can do something useful with those samples and analyze them for the development of antibiotics over time. And here you see on this graph, after the, well, basically invention or discovery of antibiotics, people have started producing this material and more, so the amount of that's being produced increases over time. Yeah, well, yes, okay, I can do it. The red one. Yeah, that's more professional, yes. Okay, so worldwide not so professional. Okay, so worldwide it's increasing, and in the Netherlands as well, you can see that over time the amount we use increases. So then we analyzed samples from this soil archive, old samples, and you can see that the amount of antibiotics that we could measure in, or the antibiotic resistance genes, so not the antibiotics, but the genes and the bacteria that confer resistance to those chemicals. They were present in the soil and they increased over time. So as a response, well, it's just a correlation, but as a response to what we're producing, the flora in the environment changes, increases.
Please talk closer to the phone, to the microphone.
Oh, sorry, yes. Okay, so we sent this to ESNT, and it took quite a while to be published, and then it turns out that they actually really liked it. And it's cited a lot, this paper. I mean, I'm not the first author. I just told them, well, we have this archive. Maybe we can do something useful with it, and everything else was done by others. But still, it's a well-cited paper. The Dutch archive was good, of course, because I'm Dutch, but in England they had an even better archive. And England also has a little bit more stringent rules on the use of antibiotics. So you can see here that the use of antibiotics, or no, the antibiotic resistance genes present in old soil samples, just like an archive just like the one in the Netherlands. You can see here that when this antibiotic starts being used, then after it you can see that the amount present in the soil increases. And you can also see that once the government decides that this is no longer allowed, then use stops, and you can see that it responds in the soil samples. And they were from agricultural fields that had been seen manure. So that was basically me telling you, be careful with samples, and if you have samples, store them. Because later on you can maybe do something useful with it that you were not aware of when you had your samples. Okay, and now what Hervé asked me to talk about, how thermodynamics can help us in the design and understanding of processes developed to protect the environment. I think it's very hard, to be honest. So basically what I do is I show you how to make those calculations, and I give you a few examples of how to apply them. So thermodynamics is, well, we all know this, I guess. It's basically the redox tower. And you can see that oxygen is a very good electron acceptor, so it's at the top, and sulphate is not such a good electron acceptor, so it's at the bottom. I mean, this is basically microbiology 101. We all know this. Well, here's another example, but in this one, the formation of methane is really at the bottom, which is correct, of course. So, I mean, that's thermodynamics. And it's not just theory, but also in practice. There are lots of papers recently about these cable bacteria, which are very exciting, of course. And what they do is they use a sulphate that's present in the deeper layers of sediments, and there's oxygen at the top, and they form long filaments, and they oxidize the sulphate that's present in the deeper layers using oxygen at the top. So really there's this redox gradient. First oxygen is used, then usually nitrate. Well, sorry for the mistake, but I copied it. Blame her. And it's a really famous journal, but still sometimes there are mistakes. Anyway, nitrate, and then manganese is used usually, and then iron, and only then sulfate. So that's the redox tower. So how did I get interested in all these things? Well, I did my PhD in Wageningen in the Netherlands. This was my supervisor, my promoter, Alex Zander, and like Hervé said, I worked on granular methanogenic sludge, so that's how I got interested in anaerobic systems. Oh, I should maybe mention that my supervisor for my master's was Willem de Zeeuw, but the big man behind everything was...
No, I can
I'm
do
sorry.
it. So
no, I should do it. Okay.
You prefer to talk here, so...
No, yeah. Gatse Lettinga was basically the professor who was supervising everything. He's not on this slide, and actually he should be. But because I was really lucky at that time, UASB reactors were just coming to, wow, how do you say this, maturity? Anyway, they were introduced and it worked well. So I did, for my master's, I worked with Willem de Zeeuw on the effects of shaking on startup of anaerobic communities, because the idea was in anaerobic communities it's a community, so the organisms have to cooperate, and then they need to be close together, and if you shake them during startup, then it delays the startup of your system, of your reactor. And that's indeed basically what we found, and that was very nice. But the other nice thing that he did was he gave me this dissertation by Heinrich Caspar, and he used thermodynamics to basically underpin what I just said, that the organisms have to be close, and then you want to know how close and what the concentrations are in those systems and how relevant it is. And he used thermodynamics to explain this, and that was for me an eye-opener, and that's how I got interested in thermodynamics. Because at that time, this was still a little bit new. I should blow my nose. Sorry, but... it was still a little bit, well, yes, kind of new. At least it was exciting, but still exciting, I think. Bryant had discovered that what he thought was a pure culture of an ethanol degrading, converting methanogen, it turned out to be actually a co-culture of two different organisms, one that oxidized ethanol to acetate and hydrogen, and the other one, the methanogen, used this hydrogen to produce methane. And the system really depended on both organisms. You could not or hardly degrade ethanol into acetate and hydrogen because hydrogen was inhibiting the system. So without the methanogen it didn't work. And the good thing was that they didn't only observe that it didn't work, but they also used thermodynamics to explain these things. And the funny thing is, that makes it a really good paper, but if you read it closely, they didn't even do the calculations themselves. They just cite a paper by Johnson Barker to rationalize this, which was of course correct, but well, I thought it was interesting. Anyway, this is a really famous paper that uses thermodynamics to explain anaerobic processes. So how do you do these thermodynamic calculations? I wrote a short, very short, how to do this, which was published in this book. And I'll just tell you basically what I wrote in this chapter. So if you do Gibbs free energy calculations, it's basically 3 steps. First one is to calculate the delta G value under standard conditions. That means that you do it at 25 degrees and you have solutes of 1 molar concentration. So 1 molar, that's your standard conditions. And if you use gases, then the partial pressure for those gases is 1 atmosphere. So that's your standard conditions. But of course, temperature is not always 25 degrees. It's usually not. So then you have to make a temperature correction as well. And finally, after you've done that, then you have to take into consideration that your concentrations are not 1 molar or 1 atmosphere, but you have to correct for that as well. So those are the 3 steps. First, under standard conditions, then, if needed, temperature correction, and then the actual concentrations. So first, the standard values for products and reactants. Well, those you can find in tables, usually, most of the time. A very famous one is this review by Rudolf Tauer, who lists all these values, also for organic compounds, and he does it in kilocalories per mole and in kilojoules per mole, and it's all at 25 degrees. And you have to remember that he uses a negative sign because almost all those values are negative. So he uses negative, so you have to put a negative in here. That's a nice one, but the problem with that one was it's only the delta G value. And if you have to make the temperature correction, which I will explain later, then you need also the delta H value. And that's not given by Tauer, But in this other review, which I like a lot as well, he gives also the delta H values. So not only delta G, but also delta H. Yeah, well, here more delta G and delta H. So in this review, the more common compounds are all listed. But if you want to go sometimes in more detail, or if you have other compounds, there are several papers by Helgeson and Richard in GCA, and they give thermodynamic data on organic molecules, hydrocarbons, kerogens, petroleum, and lots of other compounds as well that are sometimes hard to find. And one thing that people sometimes, now I sound like a teacher, but anyway, it's important sometimes, kilocalorie and kilojoules, you have to make the conversion sometimes. Sometimes people don't do it and then you get nonsense values, of course. If you have gases and you want to know values in aqueous phase, then you can use the Henry constant and this very simple RT-ln to convert delta G from the gas phase under standard conditions to 1 molar concentrations in aqueous solution. And these values are all common, of course, but you have to make sure the Henry constant is given in lots of different forms, and you need one where this is correct, where the units are correct. Well, this is an example where we did those conversions just simply using the delta H. So the Henry constant, not the delta H for enthalpy, sorry. You can do something similar with this, if you have liquids and you want to the aqueous phase, if you have a pure liquid, then you need the solubility in this RT-ln. And for crystalline compounds, it's the same. So if you have something solid and you want to know equilibrium concentrations in the aqueous phase, then this is the conversion. However, I showed you lots of tables where GF values for compounds are listed, but sometimes compounds are not in those tables. And then there's a group contribution method, and one of them is by Mavrovouniotis. That's how I discovered these things. And what you do in that case is if you have a complicated compound, or rather complicated, then you divide this up in different subparts. And those, Mavrovouniotis, for example, he has values for those different subparts, for the different groups. And then you just add the groups, and then you get your value. And there are also a little bit more sophisticated ways where you have interactions between those groups, but that's another way to get to delta G values under standard conditions. Okay, so this is a table that lists the contribution for the different groups. So, okay, this is basically what we just discussed. And then the dealing with the temperature that I told you about. If you have the delta G, you want the delta G under your actual temperature, then you take the delta G under standard conditions, your reference temperature, and you simply multiply by this factor, the actual temperature divided by the reference temperature. So that's very straightforward. You need to use Kelvins, of course, so that's something else that you can do, a slight mistake. And well, the delta H, I just told you, Hanselmann, for example, has those values, so it's very simple. And then you have your delta G under other temperatures. Now the actual concentrations, because the concentrations in your system are usually not 1 molar. You start with the delta G products and reactants, which were just said, and then the important thing is that to understand or to accept that the delta G value is basically an equilibrium constant. There's a direct relationship between the delta G and your equilibrium constant with this multiplier RT, and it's an ln. So that also helps to understand probably a little bit. I wasn't that quick, so it took me some time at the time, but basically that explains why we have this relationship, the delta G for actual concentrations is your delta G 0 or RTLN, plus RTLN, the concentrations of the products divided by the concentrations of your reactants. And if you have C times C, so like 4 times H2 for example, then it's C to the power 4 and D to the, so basically it's all high school chemistry. So this is an example. If you have conversion of acetate into hydrogen and CO2, then this is the stoichiometry. And if you take the values for acetate, protons, water, CO2, and hydrogen, the last two in the gaseous phase, then you end up with 95 kilojoules. So that means that as a function of the hydrogen concentration, the delta G is 95, plus RTLN, hydrogen to the power 4, and RTLN is 5.71. So what I just said is delta G is a function of the hydrogen concentration, which makes perfect sense. It's strongly affected by the hydrogen concentration because the exponent is 4, so it's really sensitive to the hydrogen concentration. Delta G decreases with decreasing hydrogen concentration. And that makes sense because hydrogen is a product, so the lower the product, the less product inhibition you get, so the lower the value, and the value needs to be negative to be exergonic, of course. So delta G becomes more exergonic when the hydrogen concentration is low enough. So that means that our organisms can obtain energy from the anaerobic oxidation of acetate to H2 and CO2 if the hydrogen concentration is low enough. So if you make a graph of this relationship, it looks like this, the delta G. This is the minus delta G, so that's how you get exergonic at the top. As a function of the partial pressure of hydrogen, then you get this relationship. And you can see that if the hydrogen concentration is lower than 10 to the minus 4, roughly, then the reaction becomes exergonic. So if the hydrogen concentration is higher, it's endergonic, not favorable, and if the concentration is low enough, it's favorable. And you can do something similar for the conversion of CO2 and hydrogen to methane. So that's how you remove your hydrogen from your co-culture if you want to cultivate a co-culture that converts acetate into methane. Then you have, again, in this case it's minus 131. The delta G is minus 131 minus RT ln H2 to the power 4. So this is the relation. Well, it's, again, very similar. Delta G is a function of the hydrogen concentration. It's strongly affected because it happens to be 4 again. Delta G increases with decreasing hydrogen concentration because of this negative sign, because in this case it's a substrate. And delta G becomes endergonic when the hydrogen concentration gets too low. So that's a little bit opposite to what we just had. And indeed, if you make a graph of these two, then you can see that there's a range of hydrogen concentrations where both reactions are exergonic. So the hydrogen concentration needs to be between 10 to the minus 4 and 10 to the minus almost 6. And then this centrophic interaction between the acetate oxidizer and the methanogen is favorable. And you can also see there are methanogens that directly convert acetate into methane. And that's under standard conditions. Where is it? Well, anyway, the minus 36, and you can see, whoa. You can see that this is not affected by the hydrogen concentration, of course, because acetate is converted into methane and hydrogen doesn't function, at least not in the stoichiometric reaction. So it's a zero-sum game. Either the organisms have this plus this, or it's this. So basically on thermodynamics you cannot predict whether conversion of acetate directly to methane or via hydrogen is more favorable than the other. The sum of the reactions is always the same. Well, you can also make it a little bit more complicated, but, well, we lost some time, so I don't think it's basically showing off. But not completely. This shows the range of hydrogen and acetate concentrations. You can see here the domains where both reactants or products should be for a reaction to be exergonic. So here's a domain where the conversion of hexadecane, in this example, oxidation to acetate and hydrogen is favorable if the combination of acetate and hydrogen is below this line. And then you have your conversion of acetate into methane. That's favorable if the acetate concentration is lower than this, and for the hydrogen concentration it's above this. So this way you can construct which combination of hydrogen and acetate concentrations you need for a syntrophic consortium. And this is example with either hydrogen or formate as intermediate, because sometimes not hydrogen but formate can be involved in interspecies electron transfer. Okay, pH, well, that's very simple actually, but Tower lists a value of minus 39.95, I think, or 87. And this helped me to understand that, to know that I understood the system, because why does he list this in 39.95? Why is it correct? That's basically because at pH 7, the concentration of your protons is obviously 10 to the minus 7. And if you do 7 times this 5.7 times, or 8.3 and 295, and this one, then you get 39.95. So there's no mystery behind the value that Tower lists for the protons, but it's just simply this value. And I once had a paper rejected because I used this and I said, well, at pH 7, the value is like this, and under standard conditions. And I mentioned that standard conditions was at pH 7, but the chemist said, no, standard conditions are 0 and not 10 to the minus 7. So that was the end of the story. No, really? Okay, this is the chapter. If you think that you would need it, just send me an email and I can give you a copy, or you can buy it from Springer. Okay, now some examples. The one I'm most excited about, I think it's the best experiment I personally ever did. It's not the best experiment in the world, of course, but when I was, after my PhD, I did a postdoc at Michigan State with Jim Tichy. Does it go? Oh. And we worked on anaerobic conversion of 3-chlorobenzoate. And the idea is that 3-chlorobenzoate is dechlorinated to benzoate. So this is dechlorinated benzoate. And benzoate is a syntrophic conversion of via hydrogen to methane. So if you want to convert 3-chlorobenzoate into methane, you need at least 3 organisms: a 3-chlorobenzoate degrader, a benzoate degrader, and a hydrogenotrophic methanogen. And I was really lucky because when I joined this group, there had been a PhD student, and Dan Shelton, And he had isolated the DCB1, that's the dechlorinating organism, and he had isolated in co-culture the syntrophic benzoate degrader, and he had a pure culture of methanospirillum, the hydrogenotrophic methanogen. So he had spent 4 years isolating these organisms, and then Jim Tichy told me, you put them back together. Okay, well, so that sounds a little bit counterintuitive, but actually it was really a good idea. So we had those isolates, and when you think about it, we thought about the stoichiometry and the delta G values. And unfortunately, at that time, the value for 3-chlorobenzoate was not available, so we could not calculate the delta G for conversion of 3-chlorobenzoate to benzoate. For benzoate, it was available. Tower had given those values. You can see under standard conditions it's positive, so it's again syntrophic. It needs a hydrogen remover to get low concentrations as an intermediate, and in that way the syntrophy can work. There was the hydrogenotrophic methanogen. Well, that's very negative, so together they can do it. And well, we had accumulation of acetate in our system because we did not have a pure culture of an acetate oxidizer. So that was a pity that we didn't have the value for 3-chlorobenzoate at that time, but we did the experiment anyways. But in the meantime, we found a chemist who was able to provide us with the delta G value, or the GF0 value, I should say, for 3-chlorobenzoate, and then we could do the calculation, and it turned out that when this organism uses hydrogen as electron donor, then the delta G value is actually very low, so there's lots of energy available to this dechlorinating organism. So that's, okay, I'll explain that in the next slide. So we did the experiment, we put the 3 organisms together, and of course we measured how much methane we produced, and then we also had a system where we had only benzoate, so not 3-chlorobenzoate. And to my surprise at the time, we found less methane produced when we fed the system with 3-chlorobenzoate than when we fed it benzoate. And then it dawned on us that hydrogen was actually used for the reductive dechlorination. So part of the hydrogen that was produced by the benzoate degrader was basically recycled to the 3-chlorobenzoate degrader. So it was interfering and interplaying with the hydrogenotrophic methanogen. So that was, to me, an aha moment. Ah, that's how it works. Because they had talked about, when they had their paper in Science about dechlorination, they just mentioned it, dechlorination, but they never thought really that it was reductive dechlorination. So that was the first nice thing about it. And then the energy from the dechlorination, because of, like I just said, this is a very negative value, so you think that lots of energy is available from the dechlorination reaction. So we measured the biomass that was formed in the system, and if you fed the system 3-chlorobenzoate, then there was more biomass, 6.8 grams per mole, versus when you grew the system on benzoate. So the difference was because the 3-chlorobenzoate degrader was growing on 3-chlorobenzoate. But at that time we could not do it with a pure culture because we didn't know all the vitamins that the organism needed. So we always gave it rumen fluid, and then it could pick and choose what it needed. But later someone else found which vitamins the organism needed, and when you grew the organism in pure culture with those vitamins and hydrogen and 3-chlorobenzoate, then it really grew on this reaction. So that's how we could show that the reductive dechlorination is a source of energy for microorganisms, or can be a source of energy for microorganisms. And we also did ATP measurements, and you can see that as soon as we added 3-chlorobenzoate, then the amount of ATP in the cells increases. And if you just gave it at the same time a benzoate, then it didn't change. So in the pure culture we could show that ATP was produced as well. Okay, now basically Hervé already told you this part of my story. That's how we got to know each other. And well, I guess you all know that chlordecone is a big problem in the Caribbean. When I give this presentation in the UK, I have to explain this a little bit more, but even the BBC knows that this is really a problem. So this is chlordecone, and the trade name is kepone, and there had been a big scandal in the 70s? In
the 70s,
yeah. In the US with chlordecone or with kepone. I mean, people got ill and the factory was closed, and they had to pay lots of damages, a very huge fine. So it was known that kepone was not the best compound, or not very healthy. There was a scandal in Hopewell, but there was the banana plantations on Martinique and Guadeloupe. There was an invasion of some insects, and chlordecone was used to kill those insects, but it was not very good for the soil, of course, and well, no. So the idea, well, Hervé can explain this better, I guess. So it's present in the soil, and people are worried about the soil, and maybe we have to, not maybe, ideally we have to clean up the soils. And the question is that possible? And like he said, well, maybe there are organisms that can do something with chlordecone, so we made the calculations. Well, actually, it's not we. Igor Novak, he's a very good chemist, and he knows about those caged compounds, because you can do the calculations for lots and lots of different chlorinated compounds, but with this cage compound, the structure is completely different, and maybe that has effects on the delta G values. But he had published papers on those caged compounds already. So then we asked him, could you do the same with chlorinated cage compounds? And he said, yes, I can, and indeed he did. And that's how we got this paper, basically, because the result of these calculations was that chlordecone with hydrogen, if you dechlorinate it, then you get lots and lots of energy available from the dechlorination. So in theory, based on thermodynamics, you could hypothesize that organisms may exist that can grow on this reaction. But so far, no luck. I don't think anybody has ever found such organisms.
We have somebody in the room who was one of those people who found organisms, but not doing that.
Okay, not doing that. Maybe doing that? Because more recently, I think there's a French group, and there's, well, should I say competing? And anyway, there's another group in the States, and they work together with Sarah Gaspar from Guadeloupe. And they have enriched and enriched and enriched on chlordecone for many, many years. And they find not only dechlorination of chlordecone, but they also find these other compounds in their enrichments. And actually, I recently had a master students who calculated the delta G values for these compounds based on the Mavrovouniotis method, so just based on the structure and groups. And it turns out that if you take this pathway, that there's a little bit more energy as in those intermediates than if you have reductive dechlorination. So maybe you can explain these things, but I have to check the calculations again before I dare to show them on the big screen. But I have had a student, and he did the calculations, and it looks promising. Okay, another example. My example was on centrophic acetate oxidizers. I gave you the theory already, and I cooperate with, was it this one? Yeah. I cooperate with Maria and Anna Schnurrer in Sweden, and they are very good at isolating co-cultures of acetate oxidizers. So they have, I think they have pure cultures and high enrichment as well, but they also have pure mixed cultures of acetate oxidizers and methanogens. So we grow them, or they grow them, and I just do the calculations. But anyway, they grow them as co-culture. So one of these acetate oxidizers and hydrogenotrophic methanogens, they give them lots and lots of acetate, so it takes quite a long time to do these experiments. And they measure hydrogen at very low concentrations. You can see that is like 5 or 10 Pascal. So and Pascal, 1 Pascal is 10 to the -5 atmosphere, so it's low. This is another co-culture with a mixture of co-cultures with the same methanogen all the time. And if you calculate the delta G values for those co-cultures based on the hydrogen concentrations that they measure, you can see that it's basically rather constant value. And this is the value for the acetate oxidizer, so that's about 10 to 12 kilojoule per reaction. And for the methanogen, it's slightly more, it's -20. And it's also basically fairly constant value. Okay, that was the redox tower. Okay, now how to use the redox tower maybe to design better systems. That's hard, but it's also basically a tradition. People have been doing this for quite some time, because in 1977 there's already quite a famous paper by Professor Broda in Vienna in Austria, and he was speculating that there are two kinds of lithotrophs missing in nature, at least at that time. And he did the calculations, very simple actually. For Anamox, if you have ammonium and nitrate, if you combine the two, you get nitrogen gas, and that's a very favorable reaction. This is in kilocalories, so if it's in kilojoule, it's even, well, it's 4 times more. It's a lot of energy. And indeed, people, like 40 years, 30 years later, they discovered Anamox. And they cite this paper, of course. And this paper also helped them to convince that what they were thinking at the time was actually right. And interestingly, Broda also speculated about an organism that can oxidize ammonia to nitrogen gas. And recently, people are starting to find or to make observations in nature that this process may actually be possible as well. And they call this Diramox. So that's direct ammonia oxidation to nitrogen gas. And this is a recent paper. It's really recent, because it doesn't even have page numbers, but in ES&T. And they cite observations by this group, a Danish group, about cryptic gas production in oxic riverbeds. And there's also a pure culture of an heterotrophic ammonium oxidizer. And that organism does the trick as well. But it's a heterotroph, so it's not as nice. You cannot yet grow it on this reaction. That would be the final proof. And, well, they speculate how nice it would be if you can use this organism for wastewater treatment. These are the classical ones. And if you have Diramox, then you can simply do it like this. Okay. And you can also use, apparently, electrodes as electron acceptor. But there will be a presentation, a very good presentation, later this week by someone else, so I won't go into details about use of electrodes. Okay. How to do this systematically? Well, it's, again, maybe not about how to design better treatment systems, but it's the basis for designing better treatment systems. There's a group in Nijmegen in the Netherlands. Mike Jetten is the big man, the professor over there. And they developed this scheme and they said, well, we have an organism that can use hydrogen and CO2 to produce methane, or you can use hydrogen sulphate reduction and so on and so on. So that's the redox tower. You can do the same with sulphite and with methane. And at that time, he said, well, but this one is missing. In theory, you can use methane to reduce nitrate, or you can use nitrate. 5? Okay, I'll hurry. So basically, he said, well, this one is missing and we should look for it. And if you enrich long enough and you know that the thermodynamics is behind the system, then you can do it. And that's indeed what they did. They found a consortium that can couple anaerobic methane oxidation to denitrification. For selenite, which is not that often in those redox towers, but if you look at the values, then you can see that you can reduce selenite with hydrogen. So that's a biotechnological system. And more recently, because if you can do it with hydrogen, then the question is, of course, can you do it with ammonia and can you do it with methane as well? And this group in China, they have a mixed consortium that can use methane for selenite reduction. So this is the basis for new biotechnological processes, of course. So you can just use the redox tower and look at various combinations and then decide that you should start or could start doing your enrichments. But it's not always that easy because, to be honest, I once, when I was a PhD student, I just used nitrate and methane and I said, well, in theory it should be possible. And I waited for 3 weeks, 4 weeks and nothing happened. I said, okay, nothing happens. But of course you need maybe to wait a year or something like that. That's how they developed these systems in Nijmegen. So you need lots of patience as well, not just the redox tower, but also patience. Another example is anaerobic ammonia oxidation with arsenate. So you can reduce arsenate by using ammonia. That's also something really new. And that also tells you a little bit how tricky the thermodynamic calculations can be, because I wanted to present this here. So I checked the calculations, and then it turns out that something was maybe a little bit wrong. That doesn't mean that the process is wrong, of course not, but the calculations were not, so there may be, well, not retraction, but they will send something that the calculations should be redone. But anyway, you can use thermodynamics to rationalize these things and to start enrichments. You can do selenate with nitrate. That's also something quite new. And basically, 5 minutes, perfect. That's what I tried to say today. The thermodynamics is a useful part of the toolkit to rationalize what's going on in microbial ecosystems, and that can help you to develop new processes and start new enrichments. Thank you.